Hi, Assalamualaikum. So in this lecture, we're going to talk about vibration control using an undamped dynamic vibration absorbers. So in the previous lecture, we have seen how we can control vibration using isolator. And in this lecture, we're going to take a look at what we call the undamped dynamic vibration absorbers. So before we actually go into the details, maybe we would like to know in real application what type of application that we can actually use the vibration absorbers. So let's take a look at this video. So this is in Taipei 101, where instead of calling absorber, we call it thin mass damper. So you can see that it swings. So they use it to actually control the vibration of the building. So the concept of the building Taipei 101 maybe can also be demonstrated by this video. You can actually see the pendulum is used to actually dampen the vibration on the right hand side. Alright, so that is one of the things that we're going to take a look how we actually model vibration absorbers. And it is slightly different than the isolators. Yeah, so in this lecture we want you to understand the differences between dampers, isolators, and also vibration absorbers. And you need to appreciate the merits and limitations, and also how you can actually design these dynamic vibration absorbers in order to control vibration. So in a lot of applications, we have seen that a lot of excessive vibration is actually when the system actually there is a force whose excitation frequency is actually close to the natural frequency. So it actually happens what we call a phenomenon called resonance. The vibration could be reduced either by eliminating the force or by changing the mass or the stiffness of the system so as to move its natural frequency away from the excitation. So that's the idea of this vibration absorber as well. You want to be able to move its natural frequency away from the excitation frequency. So another way to reduce the vibration is by using the dynamic vibration absorber, or simply you attach another system, okay, another spring mass system to the original system. So if you remember in the previous lecture, the whole system, the machine plus the isolator, we see it as a 1 degree of freedom system. But however, in when we actually apply dynamic vibration absorber, you attach an additional system. So you are going to deal with 2 degree of freedom system. So that's the main difference between the absorber and the isolator. So this is an example or a model where we can actually define or denote where your capital M here actually represent the machine itself. And you can see that there is input force of P naught in this case, and you actually are going to attach the absorber, the vibration absorber. Sometimes we call it also MA, with a stiffness of Ka. Yeah. So in this case, you can see now originally the machine itself is a single degree of freedom system. When you attach the absorber, it will become 2 degree of freedom system. So as you can see, the natural frequency of square root K over M of the attached absorber is chosen to be equal to the frequency of the disturbing force. So this is another thing that we have to take note. It will be proven that the main mass, okay, capital M, does not vibrate at all, and that the small system Km vibrate in such a way that its spring force is at all instances equal and opposite to. Okay, so this is one of the concept. In order to make sure that M does not vibrate, you need to make sure this is true. Okay, so when it is true, then you have zero vibration for the machine, yeah, because there is no net force acting on M, and therefore the main mass does not vibrate. I think that should make sense. In other words, if you have P naught coming in, you want to counter that P naught that actually creates the vibration. So that's why you need if you have a net force acting on it, then you will actually cancel it out. That's the main idea. So if we actually model the system just now, okay, you can rewrite the equations as in equation 1, all right, because you are writing it for the machine as well as the absorber. The second equation is for the absorber, and the force vibration of the system will be in this form. Okay, so let's say after that, you insert equation 2 into equation 1, you get equation 3. So this is just when you rearrange the terms, then you will get it in terms of in dimensionless equation as in equation 4. So let us define some of the parameters. XST is what we call the static deflection of main system. Omega A is what we call the natural frequency of the absorber, and capital Omega N is what we call the natural frequency of main system. Yeah. Maybe later on, if you take a look at the list of equations, we are using slightly different notation, but it's okay as long as we understand the concept here. Yeah. So what do we do about this? Basically, you can actually solve for A1 and A2. If you solve for A1 and A2 and rearrange the terms, you will get equation 5. So previously, you have this relationship where you have it in terms of static deflection. Then you can actually rewrite it in this term, yeah, for A1 and A2. The amplitude of A1 of the main mass is 0 when, if you look at this, because you want the machine, the main mass means it's the machine, you want it to be 0. So when is it it will become 0 is when you would have 0 divided by something, isn't it? So you want this term to be equals to 0, because 0 divided by something, you're going to get 0. So when does it occur? So you can see it clearly that it occurs when the excitation frequency equals to the natural frequency of the absorber. In other words, if you look at this expression, you want your omega equals to omega A, so that term will become 1 minus 1, so that it will become 0. So you can actually see if that's the case. So that's the criteria that we want. So that will also gives you another expressions for this relationship where the natural frequencies of the 2 degree of freedom system with the absorber in place are the values of omega such that the denominator of equation 5 is 0. So the ratio of mu, which is m divided by m, or in other words, the mass of your absorber divided by the mass of the machine, defines the size of damper as compared to the size of the main system. So beta, okay, there is another parameter, what we call beta. Beta is the ratio of the natural frequency of the absorber to the natural frequency of the original system. So the roots of the denominator of equation 5 are basically given by equation 6. So this is also another main equations that you can solve for the two new natural frequencies, yeah, where you can given beta, given all the beta and mu, you can actually solve for the new natural frequencies when you attach the absorber. So remember previously the original system is 1 degree of freedom system, okay. So after that, after you put the absorber, it will become 2 degree of freedom system. That's why now you have two new natural frequencies. So equation 6 is the equation that you would need to use. So if you remember just now, we have the relationship between A1 and A2. Since A1 equals to 0, okay, maybe we take a look at the equation just now. If you remember in equation 5, or this equation, okay, when it is equal to 0, so what will happen, this will also equal to 0, but your A2 here is equals to XST times capital K negative K over small k, so which is what we have here, okay. So this equation and this equation. So you can also see that actually KST is actually equals to your P naught. So this is what we said earlier. If you look at it physically, you can also understand that why your A2 is actually negative P naught over K, because the incoming or the excitation frequency or the input to the system that causes the vibration is actually P naught. So this is what you want to get rid. So you need to actually apply equal and opposite forces. That's why you have this negative there, okay. With the main mass standing still and the damper mass having a motion of P naught over K, the force in the damper spring varies as negative P naught sine omega t, which is actually, so this is what we said just now as well, equal and opposite to the external force. So that is how, in terms of physics, that is actually how it cancels out the vibration, okay, or that's why we call it absorb. That is how the absorber absorb that vibration. So these relations are true for any value of the ratio. So when you actually have the absorber, it has not much reason unless the original system is in resonance or at least near it, okay. So when you actually want to apply absorber, you have to take note it should be near resonant or somewhere near it, okay. Then only you can reduce the vibration. Alright, so let us take a look at equation 8. So you have this, when you actually consider omega n over omega, capital omega n here, so you can actually use equation 8 basically. Alright, so in the list of equations you have a slightly different equation. So when equated to 0, the denominator of equation 8 the quadratic equation omega square over omega a square, which necessarily has two roots. Thus, for two values of the external frequencies omega, both denominator of equation 8 becomes 0, and consequently x1 and x2 becomes infinitely large. So these two equations, or these two frequencies, are the resonant or natural frequencies of the system. So in this case, then you can see that it fulfills equation 9. So in other words, this is the same equation, okay, but now your beta equals to 1 because your omega equals to omega n, and you can actually see you finally end up with equation 9. Okay, so this is at resonant. Okay, so what happens if you have this relationship? You can actually plot the graph. In this case, you can see as mu goes up, okay, under resonant, then you would have this figure. Okay, you're going to have these two frequencies, okay, with a distance, okay, omega 1 and omega 2, omega 1, omega 2, omega 1, omega. So you can see that the distance keep increasing as you go, increasing the mass ratio. So this figure shows the main results of equation 8 shown graphically when you have mu equals to 0.2. So it's just showing that when you have mu at different mu, you're going to have slightly different distance. Okay, you can see here, for example, you have figure A and figure B, where at under the same mu, okay, you have different gaps here. Basically, the gaps here are different. You can see here the gaps are different. Okay, so I guess that's all for this lecture. Let me just wrap up. Basically, you have these conditions, okay, an absorber where you actually attach an additional system. So you're converting from 1 degree of freedom to 2 degrees of freedom. After attaching the absorber, then you have introduced another natural frequency, so you can actually use equation 6 to calculate the two new natural frequencies. And the main criteria for you to actually design your absorber is basically using this condition omega equals to omega a, because you want to make sure it actually absorb all the input, P naught in this case. And if you have a case where your beta is equals to 1, okay, means your natural frequency of your system is equals to the natural frequency of your absorber, then you can actually use equation 9. Okay, so if it's not, then that means when beta is not equals to 1, so normally you would have slight small displacement of your machine. Okay, alright, so I guess that's all. In the next video, you're going to take a look at the example problem.